Okay, so last time we were discussing about some example showing that square root of a rational number, positive rational number, which is not a perfect square, is a irrational number. Similarly, square root of a integer, positive integer, which is also not a perfect square, will be a irrational number. And in fact, we have seen the first part is okay. Second part we were just checking, and we have come to that. Suppose m is a positive integer, which is not a perfect square, which is not a perfect square, is it not? That is square root of m. Then we will show to show square root of m is an irrational number, is it not? That we were discussing. So, we have proved this by contradiction. Suppose it is an irrational number. Suppose square root of m is an irrational number, is a rational number, sorry, is a rational number which is of the form, say p by q, where p and q, where p by q is in its lowest form, p by q is in lowest form and q is not equal to 0. There is no common factor between p and q, and it is in the form. Okay. So, what we get is, and this number p by q is a rational number. So, we can identify the two integer in between this number will lie. So, let lambda plus 1 be the two integers such that lambda less than, say, p by q less than lambda plus 1. That is, what we get is lambda q is less than p less than lambda plus 1 into q. Okay. Now, from here we can say that p minus lambda q is strictly less than q. Let it be 1, because this will be required. That is what we want is less. This will be required. Okay. Again, it is given that root m, we are assuming it is a rational number which is of the form p by q. So, p square y q square is equal to m, that is p square minus q square equal to m q square, p square equal to m q square, or p square minus m q square will be 0. So, this is also second. Now, let us consider this equation. Consider the expression m q minus lambda p whole square. Consider that minus m times p minus lambda q. Okay. Let us consider this. So, basically what we are doing that this expression, if I open it, then it can be put it in the form of lambda square minus m into p square minus m q square. One can easily just verify it. Now, p square is equal to m q square because of the 2. So, basically this will come out to be 0 because of 2. Okay. Therefore, from here m can be written as, m will be written as, and this is this square, sorry, square of this, otherwise this problem will, okay, this square, sorry, m q minus lambda, this square will come. So, m will come out to be what? M q minus lambda p divided by p minus lambda q whole square, or this square, this square. So, root of m will be this. So, root of m will be of the form m q minus lambda p over p minus lambda q, just taking positive roots. Okay. Now, p minus lambda q is less than q from 1. So, from 1 what is shows that this shows, but from 1 shows that m square root of m, that is m can be written as in the form of the 2, yes, in another form a square root of m is another form where numerator is this and denominator is this, which denominator is lower than the denominator which we have assumed q, but what we have assumed p by q is in its lowest form. So, a contradiction is reached, because m under root m is written in the form of p by q, which is in lowest form, but what you are getting under root m can also be expressed into this form, where the denominator is lower than the q, less than. It means again the denominator is lower. So, it cannot be lowest form, that p by q cannot be lowest form. So, it is contradiction. So, it shows that p minus lambda q is less than q, that is denominator is strictly less than q. So, a contradiction that p by q is in lowest form, that p by q is in lowest form, is in lowest form. And this contradiction is reached because of a wrong assumption, it is a rational number. Therefore, root m is a irrational number. Okay. So, that is what we get it. Clear? So, this much we get. Now, let us come to so what is the continuum? The aggregate of all real, the aggregate of all real numbers that is rational and irrational is called a continuum. Is called the continuum. So, basically the set of all real numbers, aggregate of all the real numbers, rational is rational, we call it a continuum. Now, this continuum is complete. This is a complete set. This continuum is closed, that is completeness is there. What do you mean by this? We have got this continuum by applying the Dedekind cuts. So, when we apply the Dedekind cuts over the set of rational numbers, apply the Dedekind cuts or section, then this collection of the rational numbers, in fact, it is equivalent to the rational numbers. When you apply the Dedekind cuts, we are basically bringing this thing into form of the sections. So, each section will correspond to some number alpha. Now, this alpha is maybe a rational number or maybe a irrational number. When we apply the Dedekind cut or Dedekind theory over the set of rational number, then it basically gives you the sections, and collection of all these sections gives the real numbers, that is the continuum. because the sections which you are getting correspond to a number which may be real, which may be rational or may be irrational. So, over the rational number we are applying the Dedekind cut, but we are getting a class which is bigger than the rational numbers, because the sections which you are getting is larger than this elements itself, that is number of rational points, because the rational point will also be added there. So, this gives you the total aggregate as a continuum. Now, the question is, if suppose I apply again that kind cut or that kind sec method theorem over the set of real numbers, that is we again find the sections or cuts by using the Dedekind's method over the set of real number, whether will you get a set of numbers bigger than this set of real numbers. The question is, the answer is no. By this method we cannot enhance further the set of real number to a bigger class. We will get basically the set of real number itself. So, that is why we call it this continuum is closed. But somebody says, why we are having the set of complex number also, which is an extension of the real number. But when you talk about the complex number, this basically is generated or obtained by some other trick. What the trick is, that we are choosing the square root of a negative quantity, because if you look the complex number, how this was introduced number. The complex number is introduced basically when we look the solution of the equation x square plus 1 is 0, is it not? There is no real number, there is no real number which satisfy this equation, which satisfies equation say 1, which satisfy this equation. But this is also an equation, this may maybe some physical phenomena may be governed by this equation. So, the question is whether can we further extend the system of real numbers, not because of the cut, because cut is not helping us, Dedekind cut is not helping us to extend it, but some other method, and that method comes out to be choosing the square root of minus 1 as an imaginary quantity I. We choose square root of minus 1 as an imaginary number. And then once it is imaginary number, then we develop the set of points where it is of the form x plus I y, where x and y both are reals, and basically this will be represented in the form of the ordered pair x y, where x and y, if x takes the position of real axis, x axis, then we call it a real, and this is we called a imaginary axis. So, the position of this point x y basically is the same as x plus I y in a complex plane C, Okay. Now, this leads to a extends complex number system of the set of all complex number, which is an extension of real, because once you buy 0, then basically it gives you entire real line. So, it is an extension, no doubt, but the way you have extended the real number is entirely different the Dedekind's method, clear? We are not. So, this is a separate, and by this method when you are extending the real to complex, this collection of the complex number does not behave as smooth as our set of real numbers, because between two real numbers one can easily ordered, one can say this two given number either they are equal or one is greater than the other, but in case of the complex no ordering can be defined. In fact, if suppose the complex numbers are not ordered set or not ordered set, it means that is there no order can be defined. If Z 1 Z 2 are two complex number, you cannot say Z 1 is greater than Z 2 or Z 1 is less than Z 2. except when equal to, of course, when you say Z 1 is equal to Z 2, we assume the real part is equal to real, imaginary part is equal to imaginary. But otherwise greater than or less than will not be. In fact, we did a contradiction, because suppose there is ordering refined, suppose I is greater than 1. So, I is complex number, 1 is also complex number, because 1 can be written as 1 plus I 0. Okay. Then what happens? I 1 is positive. So, I is greater than 1 means you are assuming to be a positive quantity. So, let us multiply by I again. So, what you get? I square is greater than 1 again, but I square is minus 1 is greater than 1. So, a contradiction. It means we cannot enter. Similarly, if you assume less than, we also lead to a contradiction. Okay. So, this shows that ordering relation cannot be defined over a complex set of complex numbers. So, it is a different system, okay, different stream where we discuss the complex number, but this is a very important area also, where the all analytic function, entire functions and all these things, Cauchy, Ricci, various integrals, real integrals can be computed with the help of the complex integration. So, it is a very important field where the people can use it in the application part. So, that is what it is. Okay. So, this is now, let us say few exercise which way I wanted to give it. So that by using Dedekind cuts, by using Dedekind cuts, that if alpha and beta are two irrational numbers, then alpha minus beta is positive or negative according age alpha is greater than beta or alpha is less than beta. So, using the Dedekind cuts, we wanted to prove this part. Okay. So, let us see. Okay. Suppose we have solution. Now, alpha and beta are given to be two irrational number. So, obviously, it can be represented by means of cuts. So, let alpha is represented by a cut L 1 R 1, while the beta is represented by a cut L 2 R 2. Okay. Now, alpha is less than beta. So, here we are having this is a alpha is greater than beta. So, alpha is here, beta is somewhere here. This is L 1, this is R 1, here this is L 2, here is R 2. Now, when alpha is greater than beta, it means every elements alpha is greater than, then every number or every element, every number of R 1 or belongs to R 1 is in R 2. All the elements of R 1 will be in R 2, but every member of L 1 does not, every member of L 1 does not belongs to L 2. Is it not? That is what is it. So, every member of R 1 is in R 2, but every member of L 2 L 1 is not there. So, there may be some member which is in R 2. So, let A 1 be such a member, of L 1 which does not belong to L 2. So, if it does not belongs to L 2, that is it belongs to R 2. So, here is some say A 1, this is number A 1, okay, which is in L 1, but not in L 2. So, it must be in R 2. Let us choose a number B 2. Now, let B 2 be a number, be a member of R 2 such that A 1 is greater than B 2. Suppose B 2 I am choosing this number. Okay. So, A 1 minus B 2 is positive. B 2 be a number of R 2 such that A 1 is greater than B 2 na? A 1, oh sorry, then yes, we should write like this B 2 here, is it not? So, let it A 1, this is B 2. Okay. So, A 1 minus B 2 is greater than 0. Is this clear? Now, A 1 this alpha minus beta we wanted to prove this. So, what is to prove? Alpha minus beta is positive. So, when it is a positive number, what do you mean by that? A cut, if I apply the definition of Dedekind cuts, then a number is said to be a positive when its lower class contains some positive numbers, is it not? Yes. Then only it considered to be positive. Okay. So, lower class will be some L 3, alpha minus beta represented by a class A L 3 R 3. So, let alpha minus beta 3, alpha minus beta is represented by a section say L 3 R 3. If I prove L 3 contains some positive quantity, positive number also, then the alpha minus beta becomes greater than 0. Okay. Now, this L 3, what is this alpha minus L 3 is the sum of, so it is okay, alpha minus given by the L 3. Now, L 3 is the sum of what? Alpha minus beta. Alpha is in where? Alpha, this is alpha, is it not? And beta is here. Now, this A minus A 1 minus B 2 is positive. So, L 3 we can say, can be say like this, that L 3 is the sum of any member of L 1 and any member of minus L 2 and any member of let it be such, let us write this thing, be such that L 3 is the sum of any member of L 1 and any member of minus R 2, any member of minus R 2 and any member of R 3, any member of R 3 is the sum of any member of R 1 and any member of minus L 2 and any member of minus L 2. Let us see what is the meaning of this. We wanted to show the alpha minus beta to be positive. So, let us suppose alpha minus beta represents a cut by L 3 R 3, okay? And we are assuming that this cut is such that L 3, any member of the L 3 is the sum of the member of L 1 and any member of minus R 2. So, if we take any element of L 3, it can be written as the sum of the elements of L 1 and minus R 2, member of minus R 2. Similarly, if we take R 3, then any member of R 3 we are assuming as a sum of the member of R 1 and any member of minus L 2. Is it okay or not? So, therefore, A 1 minus B 2, what is this? Is it not the same as A 1 plus minus B 2? Now, A 1 belongs to what? A 1 belongs to L 1, A 1 belongs to L 1, B 1, B 2 is in R 2. So, minus B 2, B 2 is in R 2. So, minus B 2 will be in minus R 2, is it not? Therefore, this is the sum of L 1, this belongs to L 1 plus minus R 2, and that is nothing but L 3, that is nothing but L 3, and this A 1 minus B 2 is greater than 0, positive. So, a section L 3 R 3 which is assumed to represent the number alpha minus beta is such that it contains the positive numbers. So, alpha minus beta, therefore, this alpha minus beta is a positive cut, is positive, clear. So, that is what is it okay or not? So, just by this you can do it. Now, let us take another exercise. Okay. Specify the sections, specify the sections, the section, specify the sections corresponding to the irrational number corresponding to irrational number E. Specify the sections corresponding to irrational number E and prove that the section so specified section so specified satisfy all the requirement, satisfies Dedekind's theorem or satisfy all the postulates or axioms or the postulate of Dedekind's theorem. Okay. Because there are three postulates in Dedekind's theorem. What are they? That we can divide the number whole system into real number into two classes, lower and upper class, and each class is non-empty. Second one is that at least lower class, every element in the lower class is less than the elements of the upper class, and third is any rational number will belongs to either this class rational number or that class, like this, is it not. So, these three postulates are there. So, we can show. So, what is that corresponding to E, you first define the sections, okay, and then show that this section satisfy the condition. Okay. Let us see this. What is E? If you remember, E is the limiting value of 1 plus 1 by n to the power n. This is the E, is it not? But here we cannot take the limit because we want it in terms of the sections. So, let us say let a n is 1 plus 1 by n to the power n, where n is a positive integer. N is a positive integer. Okay. Now, let us consider the define the classes as follows. Define the lower class L as the set of those rational number x, as the set of those rational number x, set of those rational x such that a n is greater than x, a is greater than x from and after some time, from and after some fixed value of n. That is, those rational number belongs to L for which a n is greater than x for after some is number n naught, for some value of n naught, fixed value. Say after n equal to n naught, a n is greater than x, then we say x will be in L. And row upper class R, I am defining this with a upper class R. Okay. The rational number by is in upper class R if by is, or such that ki jagah if you write if a n is greater than, okay, if by is greater than a n, strictly greater than a n for all values of n, for all values of n. So, lower class I am defining the element x rational number belongs to the lower class if n, this number a n is greater than x after a certain stage, say n is in n naught, and R is the those rational number if by is greater than n for each n. We claim that this will be a, this section, the way in which we have defined will satisfy all the conditions of Dedekind's theorem. So, what is first condition is both the class L and R must be non-empty. So, there must be at least one element should be available in R from a n as well as some element of a 1, a n must be in R. Okay. Now, if we look what is n, n is a positive integer. Okay. Now, if I take n any positive integer, this sum will always be greater than 1. When n is greater than 1, this number will always be greater than 1, is it not? So, this 1 belongs to the lower class clearly. Number 1 belongs to lower class because a n which is 1 plus 1 by n power n will be greater than 1 for n greater than 1 or even equal to 1, n is equal to 1 also, you just check greater than greater than 1, this is a n is greater than x na. So, this is greater than 1 sorry. So, x is basically 1, this number will always be greater than 1 when n is greater than equal to 1. So, this therefore, L is non-empty. Okay. Similarly, x equal to 3 if I take, then all the elements of a n's are less than 3 for all n, for all n 1 plus 1 by n to the power n, whatever the n you choose, it will remain less than 3. So, 3 is an element belongs to, therefore, 3 belongs to R. So, L and R both are non-empty, non-empty. This is the first results or Dedekind shows in the section that is. Second one condition which is in the Dedekind shows that every rational number will be belongs to either L or R. So, second one every rational number p belongs to L or R. Second is to show every rational number belongs to every rational number p belongs to L or R. This we want to show. Okay. Which is obviously true, which is obvious. Why? Suppose n is greater than p for all n. P is a number, I am choosing. So, there are two possibilities, either n will be greater than for all p, or maybe n is less than p for some after certain stage. Okay. So, then n greater than p for all n, then this p belongs to the lower class, upper class, is it not? Upper class. And if n is less than, if n is for some n, is it not, p belongs, and if n greater than this is, if n is less than, what was the upper case? Yes, n is less than by is greater than n for all n. So, if n is less than p for all n, then it is in upper class, and if n is greater than p for some n, then this p belongs to the lower class. So, take any p, suppose I take p any number, say 2, then you can say 1 plus 1 by n to the power n. Then you can choose n such a way that this class after a certain stage will satisfy this condition, n greater than, because limiting value of this is 3, e is greater lying between this, is it not? Limiting value of this will be what is this? If I expand it, 1 plus 1 by 2, this is the number actually 1 plus n minus 1 and so on. So, when you take the 2 plus something, so if you take a number, if all the numbers are less than 3, say, then this number say 4, then all the numbers are less than 4. If I take a number 2, then there are some number where it is greater than. So, we can identify all the numbers which is either in lower class or in the upper class. So, this is also true. And third part is what? Every number a in the lower class is less than the lower class. So, if x belongs to the lower class, it means that x is less than a n for some n, for n greater than equal to say m onward, is it not? For all n greater than equal, after certain stage it is less than this. Okay. But if x will be in y, but in any element in y in the upper class R satisfy this condition. Condition is that a n is less than y for each n. So, if we from here x is less than a n for some n, but this is less than y if this is an element in R. This is true for every n, this is true for some n, after some m, after some n m get m, after some n onward, okay, after some m, then this will always be less than y. So, any element in lower class will always be less than the elements in the upper class. Okay. So, this shows the property. So, all the conditions are satisfied Dedekind's. Okay. All requirement of the Dedekind's theorem is set. So, this okay. Let us see the next problem. Suppose we have so that if a be x by are rational numbers such that a by minus b x whole square, a by minus b x square plus 4 plus 4 a minus x b minus y is 0, then such that then either x equal to a, y is equal to b, or then either this part or 1 minus a b and 1 minus x y are squares of rational numbers. Okay. Is basically mathematical things. Okay. Not much Dedekind cuts is required, but some well is required the concepts. Okay. So, let P is a minus x, q is b minus y. Then if I solve this a y minus b x, then we get if I just substitute these values and we will get the value to be b p minus a q, which is also the same as y p minus x q. This is what. Okay. Just if I take this p and q, then so our given relation 1. So, from given relation we can write a by minus a means b p minus a q whole square plus 4 p q is 0, or we can also write this thing as, because this is also equivalent to this. So, we can write y p minus x q whole square plus 4 p q is 0. Okay. Now, clearly if p is equal to 0, q is also 0, that is if x is equal to a, y is equal to b, then p is 0, q is 0, the equations these two are satisfied. Is it not? Obviously true, that is nothing. Now, if they are not 0, if p is not 0, q is also not 0, then one can divide by p q and one can divide the equation 2. So, from equation 2 we get the relation. Okay. We get from here. Now, we can write like this. This is our a. So, we wanted to write 1 b p plus a q whole square. If I just made the plus sign, then 2 times of this will come in picture. So, here this is when you take the minus b and this square. So, what you are getting is, you are getting this is equal to plus 4 1 minus a b p q equal to 0. Okay. Then only it is balanced. Similarly, if I take here y p plus x q whole square, then you are getting 1 minus x by 4 times of this into p q is 0. This is from 2. Now, divide by p q. So, from here we get 1 minus a b is equal to b p plus a q, a q whole square divide by minus 4 p q. But minus 4 p q from here is nothing but which is equivalent to b p plus a q divide by minus 4 p, we can write this b p minus a q whole square. Similarly, 1 minus x y we can also write in a similar way. and this will be equal to, if I put it in this form, we can by p plus x cube divided by whole square divided by p minus x cube whole square. So, what we conclude that if a first is satisfied, then also this equation is satisfied, otherwise second is 1 minus a b can be written as square of the two rational numbers. This is 1 minus a b is square of the rational number, 1 minus x y is also square of the rational number, and that is proved the result. Okay. Then last exercise let us see, it is also an interesting one. If d is a positive integer, d is a positive integer, but not the square of an integer, not the square of an integer. Mean d is a positive integer, but not the square of an integer. It means square root of d becomes that is not a square of this integer. So, what we can say is not a perfect square, okay? Square of an integer, and by is written in the form of, suppose by is x into x square plus 3 d divided by 3 x square plus d, where x is given, x is a positive rational number, positive rational numbers, x is a positive rational number. Okay. Then so that y minus x equal to 2 x d minus x square divided by 3 x square plus d, and y square minus d is nothing but x square minus d whole cube divided by 3 x square plus d whole square. Hence, so that the section of the positive rational number numbers determined by assigning to the upper class all rational numbers whose square is greater than d, and to the lower class all the other rational numbers. So that the section of the positive rational number determined by assigning to the upper class all rational numbers whose square is greater than d, and to the lower class all other rational number is not generated by a rational number. Okay. Let us see first, let us see the first part of this. I am not interested in this, because this is a routine thing. You are having the value y is given, x is already given. So, y minus x you will find this expression, y square minus d you will find the expression, just simple calculation. So, we are not interested in solving this, but this is required while showing that this section is not a rational number. Okay. So, what is the meaning of the meaning is that this is our lower class, this is the upper class. We are taking those positive rational numbers which are whose square rational number say x, such that square is greater than d, and lower class rest of rational numbers. So, this will include all negative and the remaining positive also, and positive, some positive, but here exclusively positive square is greater than d. Now, this number say alpha, we wanted to show alpha is not rational, This is our okay. So, let us see the proof is very simple, just go ahead. Okay. The upper class clearly the upper class R has no least number, because if suppose x belongs to this class, suppose x belongs to the upper class R. Okay. So, by definition, so this implies that x square must be greater than d. When x square is greater than d and the function is defined like this. So, x square is greater than d, then y square is greater than d, and here x square, so y minus s is negative. Okay. So, we get from here is as the this one defined. So, that we find by, then we find by as defined which is such that y is strictly less than x and y square is greater than d. So, if I take any number x in the upper class, then what if we are getting another number y which is lower than the x, but still it is in the upper class. This implies that y is in the upper class R. So, upper class cannot have a least number. Similarly, lower class cannot have an upper number, largest number. We cannot have the lower class as the greatest number. Why? Because the reason is, for if suppose x belongs to the class L, then if x belongs to class L, then x square must be less than d, otherwise x will be in upper class. Okay. So, x square less than d, then the y by so defined will give what? If x square is less than d, then this is positive. So, y minus x is positive. So, y is greater than x. So, again the y belongs to lower class. So, if x is in the lower class, then we are also getting another number y which is also in lower class, but greater than a. So, L cannot have a largest number. If x square is less than d, then this is positive. So, this is positive means y minus s greater than 0. So, y must be greater than x. It means y is another class, another point in lower class which is in this. So, a contradiction. Therefore, section LR represents irrational number. That is all. Thank you. Clear? Thanks. Okay.